All right. So I want to have a brief discussion here about mastery model, which is what these lesson sets are. I teach from a mastery model perspective. And I also want to talk about how important it is to work with numbers. And I think that's holding back a number of students in my class. They're not working with actual numbers enough to gain deeper conceptual awareness. So I'd like to highlight a couple of problems that we covered and why we cover them in the way or that I'm covering and why I'm covering them in that way. So let me put you on Rene Descartes so I can move around the room. And I don't think this video will take all that long, but there's some things I want to highlight. One is, why do I teach this way? Well, in 1993, I was teaching a regular Algebra 2 class. Prior to that, as an adult, I was given the challenge of the basic Algebra 2 curriculum, which was designed for students who really struggle in math. I was hired as a coach, so I've learned what I know about algebra and calculus as an adult, keeping an eye on what it took for me to break through and get some awareness of what I was working with. I think that's been very helpful in my career. But I had 6 students in 1993 on a final exam get the equation of a line wrong, and I was shocked. My grades were, if anything, the same or better than my colleagues by a little bit at that point. I was using a repetitive process at the Algebra 1 level, and I think repetition is the key to conceptual awareness and also to garner skill. That certainly is true for athletes. You know, when you're practicing, you don't ever get away like a martial art. You learn a kata, you never get away from it. You just keep trying to perfect it, trying to get better at it, and that's what belt promotions are all about. You know, you start throwing a baseball around at a young age, you never stop throwing a baseball. As you go up the ladder with that sport, kicking a ball, anything like that. It's just true. Repetition is key. And people learn at different rates. So the lesson sets I'm writing, I'm trying to keep open-ended for the students who are making the most progress. I keep throwing new material at them. And I want to do that all the way up through Calc AB. So I'm hoping that maybe 200 lesson sets from now, there's lesson set 1 to lesson set 200, and somebody who wants to take them through the foundational material can do so. I know once I went to the mastery model, well, then at some point I saw this equation very similar to this one, 5, 3, 11, 20. This linear model, which I started writing as x minus 5 plus 3, change in y, change in x, so 17, change in y, change in x. And then I went to one of my colleagues who I was learning from as we were going along, because I really didn't have a whole lot of experience with what I was teaching. I was staying ahead of the students, but didn't have a whole lot to offer. And I said to the gentleman, I said, look it, that's the same thing as 36, slight change, and still 17 and still 3. And he went to his calculators were just really coming out. I don't remember what number we were using with. I think we started with an 83, TI 83, and I don't remember what he was working with in 1993. But he went and did a quadratic regression, put it into his calculator, took him a little while, and then he said, it's the same thing. The tables matched up, and he said, I've been teaching the wrong thing for 15 years. That was his immediate statement. And so this morphed into all the 10-second graphing forms that we're trying to master in this model, in these lesson sets, and hoping that you're having some success with that. But I do know that it takes different people, different amounts of time to learn how to do anything. And if we move forward sequentially into a new topic and concentrate on that new topic, well, for several days, we're concentrating on it. And while you're concentrating on those new topics, whatever you taught before is starting to slip away. If you're not working with it, it's slipping away. Bye-bye. And that's what we see on final exams. And knowledge that just slipped away. And so the only way to stop that from slipping away, keep working with it. And I got a feeling now that since 1993 that it works, because I haven't had a single person who can't write the equational line on a final exam. I've yet to see a person who doesn't know how to do it. an occasional sign error in the numerator, occasional, because we're doing so many problems. I'll make mistakes on stuff I know how to do because I'm talking to you and trying to compute at the same time. Right? But by and large, they've proven to me time after time in class, can write the equational line. And the mastery model is there to try to make that happen for every skill and every topic. And as you gain technical or skillful mechanics, concepts usually follow. So let me just do a couple of problems that are on each lesson set and why they're there and how important it is to work with numbers. So this is a question that I ask usually in the first 5 questions of every lesson set and test. Write it in slope-intercept form. And the purpose of that is not necessarily to graph slope-intercept form. It's to make sure that people can multiply a fraction times an integer and add another integer correctly. So people get that right pretty quickly. But a lot of people struggle with minus 10/3 plus 7. A lot of people struggle with that. And if you are struggling with that, well, then you got to start somewhere where somebody knows how to do something. 2 times 4 equals 8. All right, so what's another name for 2? 4 over 2 times 4. That has to equal 8. Well, you certainly could say 4 times 4 is 16 divided by 2. That's true. You also could have done 2 into 4. You could have done 2 into 4, which is 2. And that 2 times 4 is also 8. So there's different ways to look at that. Obviously, you could have done 2 into 4, which is where that started from. All right, so that's important for students to see. It's important for students to see that I could have multiplied minus 2 times 5, which is minus 10. And then remember, I'm dividing by 3. Adding 7. All right, it's important for students to be able to realize common denominators. And you'd be surprised how many students come in now with gaps from elementary school. And certainly it's understandable. Some of the students probably were Zooming in 5th grade or 6th grade because of COVID, but the decline in skills has been happening long before that. So it wasn't just COVID. All right, there's been a collapse, and I think the collapse can be corrected if students worked with numbers early on in a working setting. In other words, not just one topic. Maybe in 1st grade, you get students a lesson set where they identify where -3 is on a number line. And you keep working on it. You keep working on it until people can do it. And then you overlearn it. Maybe you then ask students where 1 1/4 is on the number line. And then maybe you introduce squaring. You know, maybe you introduce, can somebody tell me what 5 squared is? And you actually have students count. And maybe you talk about how do you get halfway from 0 to 30 on a number line. Maybe then you ask, well, what's 1/3 of the way? And you have students actually walk it. I don't know. I'm working mostly with fractions here, right? Showing students that 1/2 and 5/10 are the same. Maybe you get some blocks out or something, but then you ask students, well, 1/3 times what over 6 would be the same. Okay, but some sort of lesson set where you're not just working with one topic, that you're working and to do a couple of problems like it each and every day to acquire some working knowledge. So what do I see for the learning stages? For students, even coming out of Algebra 1, to plot slope-intercept, point-slope form. Start a term, most people can't do it. That knowledge, if it was ever there, slipped away. So what do I see? Well, building that, one of the questions is, let's write 3 coordinates that work here. And people begin to see 4, 6 works. Then that 9, 9 changing by 5. And then we start changing this table by 5 and this table by 3. And then what do I see people graphing? Well, eventually they, when I tell them, well, why can't you just plot these points? And I'll see 4, 6, and 9, 9. And then I won't see the rest of the line because people haven't realized that you could have gone backwards 5. -1, 1 is boom. Backwards 5. -6, -4. Hope I'm not making a careless error. And then I start to see a more responsive situation. That's correct, right? But it's still working with numbers, seeing how they work. Very important. We introduced logs early on. Why do I introduce logs even at the Algebra 1 level? Because the students coming to me later had gaps and don't understand what logs are. I mean, that happened with me in high school. I got an A on this test. ln of A plus ln of B is the ln of AB. I was so happy I even remember it to this day. And I got all the other formulas that were written. Did I understand what the natural log was? No idea. Did I even know that I was dealing with a function? No idea. So that A was really an F, because I couldn't work with numbers to save my life at that stage, nor was I teachable probably, but that's a whole nother discussion. All right, so I introduced very basic log. Day one, log 5 at 25. That's what I start with. It was a discussion we had day one in this class, and it's day one in a pre-calc class, and it's day one in an Algebra 1 class for me. Start talking about math as a language and move on from there. All right, so now where are we with logs? Well, everybody's at different places. And I remember when I started logs, I wrote it this way too. I put the 25 in the wrong position because I knew logs had something to do with exponents. And so that number seemed to be in an exponential position. And so that's how I was really writing f of x. And it took a while for that 25, that parentheses, to move into the proper physical slot of writing this logarithm. And then I had some understanding. Well, the next thing is to get a whole bunch of different numbers in the parentheses. And we started working with that. We started working with 1/5. I'm not seeing it show up on graphs yet, right? Because I was asking students to graph, and I'm not seeing these logarithms correctly graph from all of my students. Some of them have it down, some of them don't. But it takes working with numbers. So people start to show the 0.5 or 25 gets me 2. I'm seeing that. And I'm seeing 5 gets you 1. I'm seeing 5 getting us a 1. And I'm seeing some students do this. And that's where some students' graphs of logs are yet. And I'm saying working with numbers is really important. So I'm hoping soon I see, well, certainly log base 5 of 1 shows up next. I'm starting to see that materialize, right? But I'm still not seeing 1/5 getting me -1, 1/25 getting me -2, 1 over 125 getting me -3, getting the asymptotic behavior where these numbers are getting close to 0. Right? That conceptual awareness isn't there yet, but the skills are improving. And students take a long time to have that process. And what takes even a longer time to understand? Differentiation and integration. So I like to introduce it, Algebra 1. No reason not to. There's no reason a student can't understand 3 times 3 is 9, and 3.001 times 3.001 is 9.006001. And there is no reason we can't do y2 minus y1 over x2 minus x1 for that situation. All right? And then the stronger students actually see at the Algebra 1 level that the derivative for x squared is 2x, because we do it over a period of days, months even. But coming out of Algebra 1, understanding rates of change of a quadratic, whoa, that's good. That's a good thing. And we don't have to wait until somebody gets to calculus to do it. All right. So what's next? Working with numbers. We already talked about how important it is for slope-intercept form, but let's go over here. Bingo, bango, bongo. All right. So working with numbers. I'm going to make a statement over here that puts these fractions together, and I want to know if that statement's right. So I look at it and I say, can I find an easy number to work with? Well, multiples of 3 here would be nice, and I can start with the number 5. That gets me 1. 9/5, that might be a better number. Let's stick with multiples of 5. Let's throw 8 in there. Oh, that's 2. 8 plus 4, 12/5. Let's try one more. Let's try 11. Oh, bingo. Even though I'm doing bingo, bango, bongo, bingo means something else right now. It means I found something that's nice. 11 minus 2, 3 divided by 3 is 1. 11 plus 4 is 15 divided by 5 is 3. Right? So if I put an 11 in there, making sure at the end of the video I'm not making a careless error. 15 divided by 5, yes, I'm taking away 3. 11, and I did just make one. I picked 11, but in my head, I put a 5 in. 11 minus 2 is 9, divided by 3 is 3. Oh, that's 0. So whatever statement I make over here, if I drop 11 into this statement, it better come out as a 0, or I made a mistake. And this is the work you do for homework. It's the work you do when you're practicing the lesson sets. It's not necessarily the work you do when I'm giving you a test, 70 questions in 70 minutes, which is going to be 120 questions in 120 minutes at the end. That's a lot of problems to do. You got to know what you're doing, and you got to trust what you're doing, and you got to work fast. So you may not have time to check, but you certainly do if you have time left over at the end of the exam. The fastest I've had an Algebra 2 student, I think, do a lesson set. I think it was 39 or 41 minutes. Did 102 problems, got 101.5, made a sign error somewhere. That's a half a point off. But 39 minutes, 120 questions, 102 questions. That was right, Algebra 2 class. That's pretty good. So, bingo, bango, bongo. And my hope is that as you do bingo, bango, bongo like this, bingo, the parentheses disappear. Bango, don't lose those parentheses. Bongo disappears. But we're not there yet because we're still making mistakes, or I wouldn't be highlighting this problem. So let's do the math. X minus 2 times 5. Because remember, in kindergarten or first grade or second grade, we proved that 1/2 equals 5/10. So I shouldn't have to say cross products here. Somebody coming into my classroom already should know about cross products. Unfortunately, that's not happening, but it should. 3 times x plus 4, 3x plus 12. And immediately, I hope somebody can see that that's where we're having our problem. The distribution of the negative. 15. And as you keep doing them, you find the shortcut. You don't have to write that parentheses. You don't have to write that one. All right, so what does this become? 5x minus 3x, 2x, minus 10, minus 12, minus 22, over 15. Let's drop an 11 in. There's 22 minus 22, 0 over 15. That's true, that is 0. I'm moving on. This is a correct answer. Okay, and that's got to be done at homework. You got to work with numbers. That's what algebra is about. Algebra is about processes, right? And how do you prove that the processes that you're saying are true? Throw a number in, any number. This is supposed to work for any number. All right, I don't care what number you put in. That is another statement for that. That's what algebra is about. So here's a problem that we're struggling with because my students are telling me the following is true. My students are telling me that 3 times 5 equals 16 plus 1. They may not know they're telling me that, but that's what they're telling me. All right, so let's actually do a little algebra. And algebra has this thing called x, a variable where I get to pick whatever number I want and to see if that's going to be true. And I'm picking the number 1. I'm going to let x equal 1, which means I'm rewriting the problem as x plus 2 times x plus 4. And over here, I'm writing it as x plus 3. And 1 plus 3 is 4. So x plus 3 squared plus 1. That's what my students are telling me is true. And if I put x equals 1 in, I get 15 on the left, 16 plus 1 on the right. And they're telling me that 15 equals 17. Now, you already know, if you've been doing the lesson sets, where the mistake is. Because if you're doing them, that means it matters to you, right? And if it matters to you to get a right answer, that's a good thing. So where's the mistake? Yeah, it's over here. -1 is what should have happened because 16 minus 1 is 15. So this was all about completing the square, which has been done numerous times. X plus 2, x plus 4, converting it into a square, x plus 3, x plus 3, getting x squared plus 6x plus 8, getting x squared plus 6x plus 9, and adjusting that number so it becomes the number 8. That's what we've been practicing. So students have to realize that, okay, when we're doing x squared plus 6x plus y squared minus 8y equals, let's get something nice, 16 and 9 is 25. Let's add 11. That you write x plus 3 squared And whatever that number is, you got to get rid of it because I don't see plus 9 over here. And when you do the binomial squaring, x squared plus 6x plus 9 minus 9, when you bring that in, then yes, it is the same as that. And then y squared becomes y minus 4, evening off the sides. And then moving the numbers over, and now you're doing a Pythagorean relationship. Keep working on things, you keep talking about things at a deeper conceptual level. Not only do you get it right, but you start visualizing the geometry behind it. X plus 3, y minus 4 equals 25 and 11. 6 as a radius. Hand of the clock moves around. These square areas change. This square area doesn't. It's 36. Right? And as one square gets bigger, the other has to get smaller within a ratio of change, which actually leads to implicit differentiation at calculus. Every single thing we're working on gets extended and expanded as we move up the ladder. But if you don't have the foundational problems done correctly, good luck with implicit differentiation when you get to calculus. But if you do have it done at an early age, then you can see those ratios of change. All right, so that was a little bit of a lecture and some thoughts on teaching mathematics. And I definitely differ from my colleagues in how I approach it. And I think there's reason to have a discussion about maybe mastery model at younger ages as a way to stem the decreases in understanding that continue to accrue. And accruing is a calculus concept. It's called accumulation. And we want to accumulate good mechanics and good conceptual awareness and not let it slip away. Stay safe and warm, Yasser. It's warming up over here. And thank you for your corrections on the last lesson set. I'm about to do another one this afternoon, and I'm a little more awake, and I'm hoping that I'll do mental math first, get the answers, and then if I make a mistake as I'm talking to you, I might catch it. All right. Safe and warm.